Hello Qiskitters, and welcome to Lecture 1 of the Qiskit Global Summer School 2024. My name is Abby Mitchell. I am the Developer Advocacy Lead here at IBM Quantum, and I am going to be taking you through an introduction to Qiskit 1.0. Okay, let's dive right in. Before we get started, I do want to explain that this lecture is going to be a little bit different from other introduction lectures from previous summer schools. So if you've attended previous summer schools, this format might be a little bit different. I am mostly going to be focusing on software, and what we've normally done in the past is focus more in the first lectures on quantum theory. So what I really recommend doing, if you haven't done so already, is as a prerequisite, go and check out John's course on understanding quantum information and computation. This will get you up to speed on a lot of the quantum information principles that are behind a lot of the software concepts that I'm going to be taking you through today. And you can check out that course either on learning.quantum.ibm.com or on our Qiskit YouTube channel. Okay, now diving into the anatomy of a quantum computing service. How does a quantum program go from being on your laptop with you as the end user through to actually being run on a real quantum device? Well, the first thing that you will need to do as a user is you will need to use some sort of quantum programming language. In this case, it's going to be Qiskit, to construct a quantum program. Then what you will be doing is using a cloud-based service, in this case it will be Qiskit Runtime, to package up that program and send it through the cloud until it hits a server in a laboratory somewhere. Then that program will go through some control electronics. You don't need to worry too much about this piece, but essentially the outcome of this step is that your program will be converted into microwave pulse sequences that can then be run on a real quantum processor. Once your program has been run, we'll get some results back, and that will kind of get propagated all the way back up the chain, back to you, the end user on your laptop. So this sort of gives you an overview at a very high level of the full process, and kind of indicates there's a lot of stuff going on behind the scenes in the cloud that maybe you as the end user aren't aware of. For the purposes of this lecture, we are just going to be focusing on this section, the stuff that you, the user, will be directly interacting with. And an example of what a final result might look like from a quantum program is something like this. You will get a series of bit strings, many zeros and ones, these in a classical format, and you will typically have run the program multiple times on the quantum device, and so you will get probabilities back of how, did you get a certain bit string more so than others. So you can see in this graph here, we're sort of visually representing how the result from a quantum program gave a lot of results that were 0, 0, 0, and a lot of results that were 1, 1, 1. And this is probably the answer to the experiment that you are trying to run. But then we also get a lot of much smaller counts of different bit strings here. And this shows that there are some errors on the quantum device. We're going to talk about this a little bit more later, but quantum devices are not perfect. You will often get, small numbers of incorrect bit strings from the outcome of your experiment, and this is why you have to run your program multiple times so that you can start to see, okay, these are where the errors are. And we'll also talk a little bit about different things you can do to prevent or mitigate these kinds of errors. Ideally, we would only want to see 2 bars in this result image. Now let's talk about what is Qiskit, the tools that we are going to be spending the majority of the time today talking about. There are many different things that sort of come under the name of Qiskit. What we are going to be focusing on today is the Qiskit SDK, which is an open source SDK for working with quantum computers at the level of extended quantum circuits, operators, and primitives. We will cover those terms in a little bit. If you want to check out the open source repository for Qiskit, you can find that on GitHub, and there's also plenty of documentation on our quantum platform that you can check out as well. We're also going to be talking a lot about Qiskit Runtime. This is the cloud-based service for executing your quantum computations on IBM quantum hardware specifically. Qiskit Runtime, the service, is not open source, but the client that you use to interact with that service is, and you can check out that repo on GitHub as well. And again, there's also plenty of documentation on our documentation platform too. Next up, you may have heard the term Qiskit patterns before. We are going to be using this quite a lot in this lecture today. Qiskit patterns is a sort of a general framework for how you can break down a problem into different stages to build a quantum program around. So you can think of it as sort of some guidelines for how you might construct a full quantum program, including everything from building your initial circuit through to running it on real hardware and getting the results at the end. Lastly, there are many other packages out there in the software ecosystem that are not Qiskit itself, but they maybe extend Qiskit, they use Qiskit a lot, and they can be useful additions to your toolbox of Qiskit SDK and Qiskit Runtime. And we generally refer to these packages as part of the Qiskit ecosystem. If you go to qiskit.github.io/ecosystem, you can see a catalog of some of, or quite a few of the projects that are in the broader Qiskit ecosystem, some maintained by IBM, some maintained by members of the open source community. And the reason that I have called this lecture Introduction to Qiskit 1.0 is that, quite excitingly, earlier this year in February, the Qiskit SDK reached version 1.0. This is a big milestone in the journey of a quantum software package, and it normally sort of brings in a new era of stability and performance for a given package. So it's really exciting that we'll be using sort of the latest and greatest package that the Qiskit SDK is today. And sort of on the other side of that coin, Qiskit Runtime was also updated with Qiskit 1.0. So we now have a version 2 of the runtime primitives. We're going to explain what primitives are in a minute. Don't worry. Just remember that there is a thing called primitives, and we are now using version 2 of them. And I will point this out in the code when we get to it later. Okay, so now that we've given a little bit of an overview of what it means to run a quantum program, what do the results kind of look like when you get them back, what Qiskit is, now we're going to start diving into some actual code. Starting with, how do we actually get started setting up Qiskit and installing it? The first thing you're going to want to do is install the Qiskit SDK, which you can do with pip install Qiskit. What I've also highlighted here is I definitely recommend also installing Qiskit with the additional visualization capabilities. This is functionality that you need, especially when you're doing the type of work that I'm going to show today for visualizing circuits, visualizing results. I recommend installing this additional add-on. We're also going to need to install Qiskit Runtime Client, which you can do by pip install qiskit-ibm-runtime. And if you need a little bit more in-depth instructions on how to do these installations, how to get your Python environment set up, definitely go and check out docs.quantum.ibm.com/start/install. That will give you a more detailed sort of step-by-step run through. There's also a video there to help you if you are not familiar with the installation process. As well as installing those Python packages onto your local machine, you will also need to make sure that you have access to IBM hardware, which you can do by logging into the IBM Quantum platform or through IBM Cloud. And again, I recommend, if you haven't done this already, go and check out the documentation in the setup channel section. We'll kind of give you step-by-step instructions on how to do that, and also how to choose if you should use the IBM Quantum platform or IBM Cloud to access IBM hardware. Okay, now that we have our package installed, hopefully we have our local environment set up. Now let's talk about how do we actually construct a quantum program. And this is the point where we want to introduce Qiskit patterns in more depth. The 4 steps you see here are the 4 main steps that make up the Qiskit patterns framework. So a single Qiskit pattern is made up of firstly mapping your problem from whatever sort of domain it's in to quantum circuits and operators, which will actually be sort of understood by the hardware. Step 2 is then taking that circuit and optimizing it for the specific backend that you wish to run your program on. Step 3 is then sending it to the quantum computer, letting it do its thing, and then getting some results back. And then step 4 is all about, now that you have these results, what sort of post-processing do you need to do to sort of analyze them and get valuable insights. So we're going to start off with the first step, mapping your problem to quantum circuits and operators. This is a whole lecture series in itself, and I think you're going to hear a lot more about this later on in the summer school, so I'm just going to talk about it at a very high level here. But essentially what this step focuses on is taking the real world problem you're trying to solve. Typically it is a very complicated mathematical problem, could be, simulating a molecule in chemistry, it could be figuring out some sort of optimization calculation. Generally, you start with a very complicated equation or some kind of numerical representation. And then what you need to do is translate that numerical representation into a quantum computing representation, which normally takes the form of a quantum circuit. And what you also will need to do as part of that process is there's typically a few different quantum algorithms that you can select to help you with that process. So building a circuit with Qiskit is a key part of this phase. And I'm just going to take a little bit of time now to sort of talk you through what a quantum circuit actually looks like. If you are familiar with classical programming, maybe this imagery is somewhat similar to you. But this image that I have here in the center of the slide this is a quantum circuit. It's a very simple one. It only has 2 qubits in it. Each black horizontal line here represents a qubit on the device. And each block here, you have different colors, they're doing different things. These represent operations that can be done on that qubit. So here, this big red square, this is a Hadamard gate. This is a really fundamental gate in quantum computing. It is the gate that will put your qubit into a superposition. The next one here, this sort of blue line and plus sign, this is a 2-qubit gate. So it doesn't just act on a single qubit, it acts on 2 qubits. This is called a controlled NOT gate. What a controlled NOT gate does is it flips the second qubit from 0 to 1, depending on what the value is of the first qubit. Then these sort of gray boxes here, these represent measurement gates. We somehow need to be able to convert quantum computing data into data that a classical computer can understand and send to us back at home on our real laptops. So to do this, we have to do a measurement on the qubit. And at the point of measurement, the qubit will then collapse to either a classical 0 or a classical 1, and that value will be recorded on a classical bit, which is represented by this double gray line. So here we have 2 classical bits, and it's recording one value from qubit 0, and another value from qubit 1. So how do we actually code the circuit that I just showed you before? Now we're going to dive into the Qiskit SDK code syntax itself. As you can see, it's based on the Python programming language, which is great, especially if you are maybe not coming from a classical software domain, maybe you're coming more from a scientific domain. Python is one of the easier coding languages to get started with. So the fact that Qiskit is written in Python makes it quite intuitive and not too difficult to pick up. The first thing that we have to do is we have to import a quantum circuit and a quantum register class from Qiskit, and then we have to initialize them. A quantum register is a collection of qubits. So for that circuit that we just saw, it had 2 qubits. So I'm initializing a quantum register with 2. And then we need to put those qubits into a quantum circuit. So we are initializing a quantum circuit like this, and then we are passing the qubits as an argument to it. Then once we have our circuit, we want to apply those gates, that Hadamard gate, that C0, those measurement gates as well. To do that, we call circuit.h for a Hadamard gate, and then we pass in the label of the qubit that we want to apply that gate onto. And we do the same for the controlled NOT gate. This time we call that function using .cx. And this time, because it's a 2-qubit gate, we're passing in the 2 qubits that we want to apply that gate onto. Lastly, we want to add a measurement gate onto each qubit. Luckily, we don't have to put in, if we know we want to measure all of the qubits, we don't have to put in every single qubit there. We can just call this measure all function, which will do it all for us. That becomes really helpful if you have a 100-qubit circuit and you don't want to list out all 100 qubits. Lastly, in this code example, we're calling circuit.draw. This is why I mentioned earlier it's important for you to install Qiskit with the additional visualization component, because that will enable you to call this draw function, which is what will sort of render this nice visual here for you. So if you want to visualize how your circuit actually looks, you're going to need to use this draw function to do that. And I'm just passing an MPL argument here. This is just for a styling thing. There's different types of styles that you can render your circuit in. MPL is just the prettiest. Okay, so what I showed you was, a very, very minimal example of what a quantum circuit, of how you can actually code a quantum circuit with Qiskit. But Qiskit itself is a lot more powerful than just that small little snippet that I showed you. And we're just going through an introduction here today, but at some point, especially through the course of the next 2 weeks and through the rest of your quantum journey, you will want to start scaling up and start using some of these much more complex functionality. And Qiskit itself has a bunch of different operations gates in its in the code base to help you with this. We have what's called standard gates. These are your very typical sort of collection of gates, like the Hadamard gate is here, the C0 gate is here, a couple of other classics. And then there's also variational parameterized gates as well. These are gates where you can submit sort of custom rotations to them. I'm not going to go into a lot of detail about that, but if you're familiar with variational algorithms, these types of gates are really important for that. Okay, now that we have gone through the step of mapping a problem to a quantum circuit, creating that quantum circuit using Qiskit, next up we are going to move on to the second step in a Qiskit pattern, which is optimizing that circuit. There are typically 2 different ways for you to do this sort of optimization step. The first one is absolutely essential, and that is transpilation, where you have to take the circuit that you created and convert it into something that can run on the specific hardware that you have selected for your computation. The other part of optimization, which is more optional, is that some people find that it's helpful to use some kind of simulation techniques to just verify that their circuit has been constructed in the right way before they make the jump to running it on a real device. So to start off with, let's talk about transpilation. To understand why transpilation is important, we need to understand that real quantum devices are subject to various constraints. The first one is this thing called a basis gate set. The circuit that you can create using the Qiskit circuit library or building your own custom gates isn't necessarily the exact same gates that you can use on a real device. A real device typically maybe only has 4 or 5 core kind of basis gates that can actually be run. So any circuit that you create, if you created an abstract circuit which uses a different gate that isn't part of that basis gate set, that gate needs to be converted into some combination of those basis gates. And this can, turn in your abstract circuit, something that looks like only one gate might actually be made up of 3 basis gates. So that can extend the length of your circuit, which can have implications for how long it takes to run and how good the results are that you're going to get back. Another constraint is qubit connectivity. This little diagram here shows sort of the layout of how qubits are actually connected on a real device. And you can sort of see here, each dot represents a qubit, and not all qubits are connected to every other qubit, and not all qubits have multiple connections. Some qubits can only be connected to one other qubit. Some qubits can be connected to 2 other qubits, and some qubits can be connected to 3. So it's really important that you need to be able to convert your circuit into something that has the correct connectivity. Make sure that you have any qubits that need to be connected to 2 other qubits are actually mapped to the correct qubit here so that you can facilitate those connections. And the last thing, we've already touched on it a little bit before, is this idea of errors. Quantum devices are not perfect. Every operation that you add, every gate that you add to your circuit has a chance of not going correctly, and it can generate an error. So there are other optimizations you can do to reduce the chance of these errors occurring. For example, reducing the number of C0 gates that you have. 2 qubit gates tend to have a higher chance of erroring than single qubit gates, for example. Or just reducing the depth of your circuit. So if you have a circuit with only 10 operations deep, it's going to probably give you better results than if a circuit that is 20 gates deep. So all of these things sort of, mix together to, form the things that you want to be considering when you are trying to optimize your circuit. And this kind of presents this challenge, right, where you want to be able to run an abstract circuit on a specific quantum device, which has a specific connectivity, a specific basis gate set. And the way to kind of do this is through transpilation. This is when you are essentially converting that abstract circuit into what is called an ISA circuit, an instruction set architecture circuit. You will see this term come up a lot, so burn it into your brain. An ISA circuit is a circuit that is optimized and specifically runnable on the device that you have chosen. Digging into this idea of transpilation a bit more, there are some other terms that you should be familiar with, and that is the idea of a pass, the idea of a pass manager, and the idea of a staged pass manager. It's also helpful sometimes to think of this in terms of an analogy. I quite like this orchestra way of this orchestra metaphor. Starting with a pass, this is a single transformation that you might make on a circuit. And you can think of that as maybe a single instrument in an orchestra, like a violin, for example. A pass manager is a list of those transpiler passes that are grouped into a single logical unit. So if a pass is a violin, then an instrument section might be the string section of an orchestra. And finally, a staged pass manager is a list of pass managers. each one representing sort of a discrete stage in your transpilation pipeline. So you can sort of think of this as the conductor of the orchestra, the one that pulls all those different sections together and helps them play in harmony. So how do we actually do transpilation with Qiskit? Luckily, there is a lot of built-in tooling that can do a lot of this for you out of the box. But what you should also know is the example I'm showing you here might just be a very sort of simple example. What's really powerful about the transpiler in Qiskit is that it is very customizable. So you can do the things that I'm showing you here from scratch yourself and make your own tweaks and your own decisions if you feel like you know better than what the transpiler could do for you. So let's dig into this code a little bit more. You should be familiar with this section here. It's the same as before, where we just created a simple quantum circuit. This next section here is the important bits that's showing you the transpilation. First of all, we need to initialize the Qiskit runtime service, because remember, we are going to be sending this program eventually to an IBM Quantum device through this Qiskit runtime cloud service. And so we need to initialize this service, and we want to be able to select the backend. Remember, transpilation is converting your circuit into something that is specific for your backend. So you need to have chosen your backend ahead of time to be able to do this transpilation. So here what we're doing is we are calling service.backend, and we're passing the name of the backend that we've chosen for this example. It's just IBM Brisbane. Then what we're going to do is create a pass manager. Remember, a pass manager is a list of transpiler passes. And Qiskit has a very helpful sort of beginner pass manager function for you. So if you aren't yet confident enough with transpilation to construct your own combination of passes, Qiskit has this generate preset pass manager for you, which will sort of do it automatically. And the important things that you want to pass to this generate preset pass manager function is, first of all, the backend, so that we know that we're transpiling for this specific device that we're going to be using. And next is the optimization level. This is a sort of a blunt way of you saying how good do you want your circuit to be optimized through this transpilation process. You can start with, I think there's 3 optimization levels, and the higher your optimization level, with level 3 being the highest, the more optimized your circuit is. But that does come with a caveat of it taking a lot longer for the transpiler to actually generate that optimization for you. So if you have a really big circuit, it's probably going to take you a while to do that transpilation process if you're going for that higher optimization level 3. And then finally, to actually generate this ISA circuit that we can send to our device, we need to call passmanager.run and then pass our original circuit that we created to it. And here I've just drawn for you what that might look like. As you can see, this circuit looks quite different from that initial Hadamard and CNOT gate that we had at the start. So what are the different types of transpilation paths within any form of transpilation? There are actually 6 stages to transpilation. 1, 2, 3, 4, 5, 6. Don't worry about memorizing this all right now. There is plenty of documentation that you can have in your back pocket. Just have it on hand to remind yourself. I'm just going to go through them very briefly. The first stage is initialization. This is quite a smaller stage. It doesn't do an awful lot. Mostly what this stage is for is converting multi-qubit gates into 1 or 2 qubit gates. When you're creating an abstract circuit, you might be able to add a gate which has that spans 4 or 5 qubits, multiple qubits. But in reality, the device can only handle 2 qubit gates. So that multi-qubit gate needs to be converted to 2 qubit gates. Next up is the layout stage. So what happens here is the qubits in your abstract circuit are mapped onto physical qubits on the device. And then this then moves on to the routing stage, where sometimes when we've laid out the qubits, the ones that need to interact aren't next to each other. So we need to insert swap gates into the circuit to enable interactions between qubits that need to interact with each other, but maybe aren't physically located next to each other on the device. Step 4 is translation. This is where every gate in your circuit is converted into a basis gate from that basis gate set that I mentioned before. And each device might have a different basis gate set. So this is something that's very specific to the device. The 5th step is some further optimizations. Things and different things can be done here. For example, you might rewrite the circuit to make it shorter. Remember, we said that the shorter the depth of your circuit, probably the less chance there is of errors happening, because the qubits have a finite lifetime before they decohere. So you want to try and get your operations done as quickly as possible, so you have the greatest chance of that qubit sort of staying coherent within that time. And then lastly, we have scheduling, which is just when you add certain delay instructions here. So you need to, when you're running the circuit, sometimes you need to make sure that certain operations are done in a certain sequence between the different qubits. So sometimes you need to add delay instructions to say, okay, you have to wait before we can run this operation on the circuit. Apart from the transpilation code that I showed you earlier that just uses the Qiskit SDK, there are some additional tools out there that are useful for transpilation that you might want to explore in your own time. The first one is quite new. It's the Qiskit Transpiler service. This is a cloud-based service for doing transpilation, and it also includes some AI-powered transpiler passes as well, which is pretty cool. Then within the broader Qiskit ecosystem, there are many different packages or projects out there that might optimize certain bits of the transpilation pipeline. Circuit knitting toolbox is one example of some optimization that you can do as a package that you might want to go look at. And lastly, you can also write your own transpiler plugins. I mentioned earlier that the example I showed you was just a really basic example. But what you can do is, if you learn more about transpilation techniques, you might decide to create a transpiler pass that you think is better or more customized to your use case than something that Qiskit provides, and you can create that yourself. And Qiskit's interface is very pluginable, so you can turn your pass into a plugin that you can then use directly in your Qiskit transpilation pipeline. Okay, now that we've covered the basics of transpilation, let's move on to the other type of optimization that you might do in that step of a Qiskit pattern, and that is verifying your circuit with simulation. There are a few different simulation tools that you probably want to be aware of. The first one is the Qiskit SDK has reference primitives. We're going to talk about primitives a little bit later, but in Qiskit itself, it's just good to be aware that Qiskit has its own version of primitives that can do exact simulation, but really only for very small circuits, and you can't simulate any type of noise with them. So this is really just for very basic testing out if you've initialized your primitive properly, that type of thing. The next option that you have is the Qiskit runtime local testing mode. This is a useful tool if you want to test out how to interact with the runtime cloud service. And it provides a number of fake backends that sort of mimic the real devices that IBM has, obviously not to the same quality level, But it's useful for example, when you're doing transpilation, maybe you want to use those fake backends just to like test out how you're doing transpilation and things. And sometimes it's useful to be able to mimic a specific backend, including the type of noise that is present in that device. And here's a code example of how the same the same kind of transpilation process we showed earlier might work, this time with the fake backend instead. Lastly, we have Qiskit Air, which is a Qiskit ecosystem project. This is maybe a slightly more powerful simulator than the other two options. You can do slightly larger circuits. It also supports stabilizer circuits and noise models as well. But it is important to note that there is an inherent problem with using simulators, and that is, the reason why quantum computers exist in the first place is because at a certain size of computation, classical devices just don't work anymore. Maybe if you have a pretty good Mac and a pretty simple program, you could simulate maybe 50 qubits. Really depends on the specifics of the circuit you're trying to simulate. But this is where, simulation really just becomes a stepping stone to get you to hardware. Some things that you need to think about is like if you're trying to scale up to utility scale circuits when you're using 100+ qubits, simulation is not going to be able to get you the answers that you need. So then the question becomes, how do you, test out that your, 100+ qubit circuit is actually going to work properly when you send it to the real device? And there's sort of two different ways that you can generally approach this problem during that optimized step of a Qiskit pattern. The first way is maybe you want to test smaller versions of your circuit, kind of break it up into chunks or simplify it so that it's something you can test out, just to kind of give you an intuition for did you construct your circuit in the right way. Another option is changing the circuit to something that becomes classically simulatable. This is what's known as a stabilizer circuit or a Clifford circuit. It's a circuit that's made up of a very specific combination of gates that can be efficiently run on a simulator. But obviously, if you're modifying that circuit, it's not a one-to-one, it's not going to be exactly like the original circuit you had. So the answer you get at the end is going to be an approximation of the correct answer, but only when you actually run it on the real device will you get the correct one, the one that you're looking for. So that's just some caveats with simulation. They can be a great tool for debugging your quantum program, but they are not ever going to be, a really good replacement for utility scale quantum computation. Okay, now we're going to move on to the third step in a Qiskit pattern, and that is finally we are executing our quantum program on a real device. This is where primitives becomes an important concept to understand. And what a primitive really does is it encapsulates the output of a quantum circuit. And there are two different types of primitives that are available to you through Qiskit and Qiskit Runtime. The first one is a sampler primitive. This is the primitive you want to use if the output that you want from your computation is a series of bit strings mapped to how many counts you got. So if you ran the circuit 100 times, how many times did you get a 0-bit string? How many times you get a 1-bit string? The sampler primitive will produce the output in that format for you. And then next up we have the estimator primitive. The output of an estimator primitive is an expectation value of an observable. So this really depends on the specific of the problem that you're trying to solve with your quantum program, and this can be very domain specific. So for example, if you're trying to solve some numerical problem in high energy physics, maybe the observable that you are looking for is the spin of an electron or a system. And so your expectation value is what you're looking for here. It's just a single result that you get. An important distinction when you are calling a sampler primitive versus an estimator primitive. A sampler primitive, you want to make sure that your circuits include measurement gates, whereas for an estimator primitives, you don't want measurement gates in that circuit. So what does it look like in code to run a quantum program using the primitives? The first example I have here is of the sampler primitive. So here we haven't used we're not using the same circuit we used earlier. Instead, we just chose a standard circuit from the Qiskit circuit library. So again, a really useful feature of Qiskit is it has its library of pre-built circuits, which is perfect for us in this small example. We're just sort of generating an IQP circuit with this selected number, random number of with 127 qubits and this sort of random configuration here. We have also initialized the Qiskit runtime service. I showed you an example of that earlier as well. And this time when we're selecting a backend, we're going to use this helpful function from the runtime service to select which of the quantum devices is the least busy and is not a simulator, and it has to have 127 qubits for this example. This is a great function to use, especially because there are a limited number of quantum devices out there in the world and everyone wants to use them. So normally there can be, you might have to wait in a queue before your program actually gets run. So by using this least busy function, you will select the device that has the shortest queue that you have access to. So it could save you a bit of time. So we have this circuit. We have done our transpilation just with the basic generate preset path manager option with optimization level 1. We saw that earlier in the transpile section. And then this final step here is where we are actually initializing the sampler and we are passing the backend to it. And then to actually run the execution, we're going to call sampler.run, and then we're passing our transpiled circuit directly to it. And then once it's done its thing, it's finished running, then we might want to retrieve the results to do some post-processing on it later. And we can call that by calling this job.result function here. When you send a single program with a primitive, we call that a job. So you've sent a single circuit to be run. You maybe are running it multiple times, but it's just one instance. We call that a job. Another thing to call out here, remember I mentioned that we have a new version of the primitives, version 2. You want to make sure when you are importing from Qiskit IBM Runtime that you are importing sampler v2 as sampler if you just want to change the name so you're not having to type out sampler v2 every time in the code. So just watch out for that if you might come across older code examples online. Always check the imports and make sure that you are using the latest version for your code. Okay, now we've just seen how to do things with the sampler. Now we are going to see the same thing, but for the estimator. The way we've constructed our circuit is a little bit different. We're still using this IQP circuit with this random emission and 127 qubits. But the difference here is we're also specifying an observable that we want to generate an expectation value for. In this case, we're using the Pauli Z operation. We're doing transpilation the same as before, but we have an extra step here for the observable. We need to call this apply layout function. And then lastly, we want to call estimator.run. And this time we're going to pass not only the ISA circuit, but also the ISA, the transpiled observable as well. This input is called a primitive unified block. I'm kind of glossing over it a bit now. That's because in your next lecture, in lecture 2, you should be going into a lot more detail around the structure of this pub object. And then once you run it, you can get the results the same as you did before. And just note here, we don't add any measurements to this circuit as well. Okay, so in addition to the basic primitive structure that I just showed you, you can also customize certain behavior of your runtime primitives as well. The first thing is the number of shots. I think, as I've mentioned a couple of times now, when you actually run your circuit on a device, you probably want to run it multiple times so that you can see at the end where there might be some errors that you can get rid of. Something to be aware of is that the more shots that you have, the more you can reduce the statistical error, but it does mean it takes you longer to run it on the real device. So you want to be conscious of that. Depending on how much QPU time you have, the more time you're using, obviously the more expensive it is. Another technique you can do is some error suppression. There are some built-in error suppression techniques within Qiskit Runtime that you can toggle. One example is dynamical decoupling, and what this does is it reduces the chance of decoherence on the qubit itself. The caveat is that it's not always possible because it requires some delay between different gate operations. So if you need to run an operation directly after and you don't have much time between them, then it's not possible to use dynamical decoupling. And lastly, we have some error mitigation techniques. These are techniques that reduce the effect of noise after you've gotten a result from the device. So it's not changing how things are run on the device itself. A couple of examples of error mitigation are T-Rex and ZNE. These I'm not going to go into a lot of detail about them because you're going to have quite a lot of depth on error mitigation in later lectures. Just for now, be generally aware of the idea of error mitigation and some of these techniques that we will explore in more detail later. Error mitigation is a great technique, but the one downside of it is it normally has additional computational overhead. You normally have to end up running additional circuits or using more classical resources as well. So there's always a trade-off. As well as the sort of just the basic primitive jobs that you can run, there are a couple of different execution modes that you can use with runtime. And these are really helpful when you start scaling up to much bigger computations. As I mentioned, when you're just sending off, sort of like a single circuit to be run, we call that a job. But you can also combine multiple jobs into a batch. So if you need to run multiple jobs in a row, it's more efficient for you to use this batch mode. And sessions is similar if you have multiple jobs you need to run, but it's more iterative. So going into a little bit more detail on that. Some of the benefits of batch mode, as opposed to just running a single job back and forth, is that runtime is sort of clever enough to do some kind of additional classical processing with batching that helps you get your individual results sooner. So it's slightly quicker than if you just were like running single jobs back to back. If you run those jobs as part of a batch, runtime can do some clever things behind the scenes to kind of get you the results back quicker. And to initialize batch mode with a primitive, here we just have an example of maybe we have 100 circuits that we want to, and each is a single job, and we want to get results for all of them. What we can do is use with batch and then pass the backend, and then initialize our sampler, and then call sampler.run with those circuits for every single circuit in our array of jobs, of circuits. So it's a little, if you're kind of familiar with this, with Python already, this sort of language might be something you're already familiar with. You just want to remember that, you know, everything that's happening within this batch context is what is going to all be sent together as part of that batch mode. Sessions similarly allow you to send multiple jobs in sort of a single kind of workload. But the difference with sessions is that it will allow you to, with certain algorithms, especially variational ones, what you might need to do is send a job, get the result back, and then based on that result, send another job. So in that instance, batching wouldn't work because sometimes, you know, there's not enough time to wait to get the result and then send off the next job. Batching just like sends it as quickly as it can. For sessions, it's tweaked a little bit so that you can do that classical post-processing before the next job gets sent off. And this is still, slightly faster than if you were going to run your batches run your jobs just a single job. Sessions does it a little bit more efficiently. And to initialize a session, very similar to batching, you just call with session, pass the backend, initialize your primitive, and then run it as you normally would. Okay. We have completed the third step of the Qiskit pattern, and now we're on the home stretch. We've gotten our results back. What sort of things can we do for post-processing? The first thing you probably are going to want to do is visualize your results somehow. You can do that with a bunch of different features within the Qiskit visualizations module. For example, there's a nice plot histogram function you can call, which is what will sort of group your results and display them nicely in that image that we showed, right at the start. Another post-processing technique is something called post-selection. This is where maybe you can filter out some of your results that you know are going to be incorrect based on some prior intuition you have. So let's say maybe you get sort of like in this diagram we can see here, like, oh, there's like these bit strings, we're pretty sure are errors. So a post-processing step would be to like filter out these results that you know for sure are not the correct results and just leave you with the results that you know are the correct ones. That's called post-selection. Another post-processing technique is circuit knitting. This is a really cool technique that you can go and explore with that ecosystem project called the Circuit Knitting Toolbox. This is where during your optimize part of your Qiskit pattern, you can decompose your circuit into smaller chunks. That's called circuit cutting. Then you execute those circuits as you normally would in the third step of the Qiskit pattern. And then lastly, in this final post-processing step, you can then stick the circuit kind of back together to reconstruct what the original circuit outcome would have been. That is a very gross simplification of the process, but it's all that I have the time to explain in a single slide for you. I really recommend going and looking up the Circuit Knitting Toolbox, and they have more tutorials and examples of how that process works. And so there we have it. We have gone through all 4 steps of a Qiskit pattern. Please don't worry if a lot of this went over your head. This is just the first lecture in the summer school. You will have plenty more lectures to go through where you'll kind of be exploring the same concepts and going into a lot more depth than what I've just shown you here today. Today was just sort of getting you exposed to an overview of what it means to run a quantum program using Qiskit, using the latest versions. And I hope I enjoyed this lecture and are excited for the rest of the summer school. If you want to go for a deep dive on any of the things that I have talked about today, I really recommend checking out these websites here. docs.quantum.ibm.com gives you a lot of technical documentation on Qiskit and IBM Quantum services. Learning.quantum.ibm.com gives you full-on courses and tutorials. That's probably a lot more like deeper dive type of content. And then lastly, we have YouTube Qiskit channel where there's all sorts of stuff there. There's lectures, there's funny videos, there's community updates. And yeah, I really encourage you to go and look at these in more depth and enjoy the rest of the summer school.